morning, students. Hope you're following the previous videos. Last classes, we studied the reflection with different types of mirrors, plane mirrors, spherical mirrors. In the spherical mirrors, we have concave, we have convex mirrors. We studied image formations, right? Now, today, we are going to study another phenomena for light that is called as refraction. Okay, what do you mean by refraction, right? So whenever, if you observe these pictures which I have given, one thing you should notice, right? The light which is coming to us, or the way we can see over here, it is passing through two different media. Okay, for example, in this glass, when we are seeing this glass, when we are seeing the birds from the glass, we see it through the water. Secondly, this log of wood. Okay, this is a beautiful picture wherein both the phenomena, your reflection and refraction, both of them are taking place at the same time. If you see the log of wood which is above the water is getting, you can see the shadow over here. This is the shadow, okay? And the half part of the log of wood which is immersed inside the water, why isn't it appearing to be straight? Basically, the way this line is given, this should be the positioning of wood, but when we see it through water, it is coming in this way, right? So why is this happening? Have you ever imagined why is this happening? Secondly, see these now. Is the spoon, is the straw which is placed in the glass, is it bent or is it crooked or is it broken? If it is broken, then why are we using it? Right? If you see these colors of the wall through water, why is it appearing like this and why is it not appearing in a pattern the way it is there in the wall like this? Okay, if you see the straw over here, if you observe it over here, this is looking to be crooked. Again, the spoon, basically the spoon should go from here. Okay, the spoon should go and then it should continue from here. But then why isn't this not happening? This place of the spoon is displaced, right? So why is this happening? Okay, this is happening because of the phenomena of refraction, right? So what is refraction? Refraction is basically tendency of the light to bend at separation of two media. That means whenever ray of light travels from one medium to another, till now, during reflection, we were only dealing with one type of media, that is the ray of light is passing in air, it is bouncing on the mirror, spherical mirror, and it is getting reflected back. Okay, all this entire phenomena was happening only in one medium. Now we are going one step ahead. We are going to study how light behaves when it travels from one medium to another. So just to give an idea, light basically bends. Okay, for example, this is if you see this entire picture, here it is water. This is your water medium, right? This is water medium, and this is your air medium. Now this line, okay, which is touching the water and the air medium, it is called as interface of the medium. Okay, now when ray of light which is coming from the sun, it is touching this interface. Now what is happening at this interface? This is the point of incidence. At the point of incidence, what do? At the point of incidence, we always draw a normal, right? If you see this blue line, this is your refracted ray, because why refraction? I am telling refraction will be there only when a ray of light passes from one medium, basically to be precise, it should be one transparent medium to another transparent medium. Okay, so refraction will happen only when the ray of light goes from one transparent medium to another transparent medium. Here we are dealing with a pair of media, that is air and water. So if you observe, this ray of light which is coming from sun is getting bent. Okay, so this is the bending phenomena which is happening. So now what is refraction? Refraction is basically this bending of light, right? So whenever a light travels from one medium to another, it bends. Okay, so in this case, air media and water media, these are the two media which we are dealing with. So if you observe, ray of light is bending towards the normal. But why is it bending towards the normal? Right, towards the normal it's bending. If you see, normally if bending wouldn't have been there, this ray of light should have passed like this. It should have passed like this without bending, right? But as the ray of light is passing from one medium to another, it is bending, and this phenomena of bending of light is called as refraction. But again, why is it bending towards the normal? Is there any rule which governs this bending? Okay, what makes it bend towards the normal? Why is it not bending away from the normal? Right, so we will answer these questions in the coming slides. Okay, now in order to understand refraction, we first of all uh, we should know certain basic common terminologies that we use already. After uh, studying the concept of reflection, we are well aware of these terms. Incident ray, the ray which is coming from the source of light, that is called as incident ray. Now here, instead of reflected ray, we are going to use the term as refracted ray. Refracted ray, when this incident ray passes from one medium to another, it gets refracted from the interface. Okay, so this blue one is your refracted ray. Obviously, what will be angle of incidence? Angle of incidence will be angle between the normal and the incident ray. So if you observe, this is your angle of incidence. The yellow one is called as now angle of refraction. Okay, refraction is again angle between normal and the refracted ray. It's a rule. It's, we know always, this is, if this is the point of incidence, at the point of incidence we always draw a normal, right? So these are the basic terms which we should be well known with for to study refraction. Now we know, I have already explained you what is refraction. What is refraction? Refraction is basically bending of light when light travels from one transparent medium to another transparent medium. In other words, when light travels from one transparent medium to another transparent medium, it bends. This bending phenomena is known as refraction of light. Okay, now we just saw in that picture that the light is bending towards the normal. But what makes it go towards the normal and what makes it go away from the normal? So these are the two most important things that we need to understand. So in the picture that you just saw, in this picture, from where to where the light was going? The light was going from air to water. Okay, so this is your air, this is your water medium. Okay, now can you tell me the density comparison for air and water? Obviously air is more optically rarer medium, and water is a denser medium. So here we are going to use optical density. Okay, we are going to compare the optical density of these mediums, right? See now, when you observe the first phenomena, where is the refracted ray going? The refracted ray is moving or bending towards the normal. So when it bends towards the normal, when will it bend towards the normal? When the ray of light travels from an optically rarer medium to an optically denser medium. This is my incident ray. At the point of incidence, I am drawing a normal. As it is going from a rarer to a denser medium, it will move towards the normal. Understood? These are the rules, or this is the phenomena which is taking place. On the contrary, if you observe the second diagram, uh, This red one is your incident ray and the blue one is refracted ray. So basically this incident ray should have gone just in a straight line, but now it is moving away from the normal. So what makes it go away from the normal? So when a ray of light travels from a denser medium to a rarer medium, so this is the ray of light which is traveling from denser medium to the rarer medium. At the point of incidence, I'm drawing a normal. It will go away from the normal. Normally it would have followed this path, right, in a straight line, but now this one is going away from the normal. So two things to understand and to keep in mind over here. Whenever a ray of light travels from a rarer medium to denser medium, it will move towards the normal. Whenever a ray of light travels from a denser medium to a rarer medium, it will move away from the normal. Right? So two things to remember. Now, what was refraction? Refraction was bending of light when light travels from one medium to another. Now, let us see refraction through a rectangular glass slab. What is a glass slab? A glass slab is a solid medium. Okay. As compared to air, how is the glass slab? The glass slab is an optically denser medium. The density of glass, being a solid, is more as compared to the density of air. Right? So let us see this. Again, this is very important from exam point of view. An entire 4-mark question will come. Explain the refraction through a rectangular glass slab. So along with the explanation, you should be able to draw this diagram as well. Okay, so now the first medium is air medium. This is your glass medium, glass, and again air medium, right? So now let's consider a ray of light which is passing from this is your incident ray. Okay, so now this incident ray, now what, this is the interface. So now I'll just try to name this glass slab as, let this be P Q R S. The glass slab is PQRS. This is the point of incidence. Let the point of incidence, first point of incidence, be O. And now it is going to be refracted, and let this be another point of incidence, O dash. This perpendicular line is your normal. So let the first normal be N dash, and the second normal be M dash. Let okay, let A, B, C, and D. Okay, I'll do that. B. So let AB first of all be your incident ray. Now, as AB is incident, at the point of incidence, we draw a normal. Can you tell me where will the refraction be, or where will the light be bent? How is, from where to where the light is going? The light is going from air to glass. That means it is going from a rarer to a denser medium. So hence it is going to go towards the normal. Okay, so it has bent a little bit towards the normal. So for that, what we can do, I will make this ray a little bit. This is my incident ray, right? Now, obviously, the angle which the incident ray is making with the normal, that is called as angle of incidence. The angle which this refracted ray is making with the normal is called as angle of refraction. So this blue one, the blue ray, is your refracted ray, right, which is going towards the normal. So in the first phenomena, can you say that angle of incidence is greater than angle of refraction? Yes, for the first two refractions are taking place over here. One is at PQ interface and another will be at SR interface. Now what happened is, now this refracted ray is again coming in contact with the second interface, that is the SR interface. Interface is the, you can say it's the plane where your medium is changing. Now at the SR interface, again the medium is changing. It is going from glass to air. Now glass being a rarer medium, air being, glass being a denser medium, air being a rarer medium. Can tell me where will this ray get bent? the ray or refracted ray of light will bend away from the normal. So if I take one more ray, so now this is going to go away from the normal. So this green ray is your another refracted ray. So what name do we give to it? We give the name as emergent ray. So you can consider as the white one is the first ray which is incident, that is called as incident ray. The yellow one which is there inside the glass slab, that is called as the refracted ray. Okay, and the third one which is again coming out, that is called as the emergent ray. Emergent ray, right? Again over here, this is your angle of incidence, and the green one will be your angle of refraction, but we call this green one as angle of emergence, that is E, and this inside angle of incidence as R only, because as both of these angles being inside the glass slab only, n dash, m dash, these both are perpendiculars, that means they are parallel to each other, these angles will be equal. So if I call this angle as, I can say I2, this being I1, this is first angle of incidence, second angle of incidence. This is R1, and let this be R2, right? So I can say that angle of refraction R1 is equal to angle of incidence I2. Okay, so both of these angles being inside the glass slab, they are going to be same. On the contrary, again, now this first angle of incidence and the angle of emergence which is over there, these are in which medium? These are in air medium. So both of these being in air medium, these two would be equal. So I can say that angle of incidence, the first angle of incidence is equal to angle of emergence. We call this angle of emergence as the second R2 because the refraction has taken place the second time over there. Okay, understood? So these are the basic things that we need to understand regarding your refraction through a rectangular glass slab. So if I have to name this particular ray, so how will I do it? So let this, I have already given this, let this A, B be the incident ray, B, C be the refracted ray which is inside, and C, and let this point be D, be a ray which is going again outside. Air is a rarer medium, glass is a denser medium, right? Again it is coming out in air, again it is going into a rarer medium. So when ray of light travels from rarer to denser, the refracted ray is moving towards the normal, like over here. In the second refraction, the ray of light is moving from denser to rarer, so it is moving away from the normal. Okay, as far as the second refraction is concerned, I can make a conclusion that this angle of incidence, so over here, this I1 was greater than, can I say it, it is greater than R1. Okay, yes, R1. And in the second one, this angle of incidence I2 is less than the angle of emergence R2. And I have already given an explanation for that. Okay, so if you see this glass slab over here, this is the path where it is moving. This is the point where it's getting refracted, and then this one is again your emergent ray. Now, if the ray wouldn't have got bent, okay, if imagine that this first incident ray AB was just going like that itself, right? So now where would my the original incident ray would have been? So if I just extend this original incident ray like this is your orange line. If I just extend it like this, and if I compare it with the green line is the last emergent ray because of the bent light. These two rays are always parallel to each other, right? These two rays are parallel to each other. Okay, now they are parallel, but have you seen the difference? The emergent ray is not following the same path. There is a gap. So now this gap which is there, this is the gap. This gap is called as lateral displacement. Right, and it is also denoted by D. This gap is called as lateral displacement. Okay, so this is how refraction through a rectangular glass slab is going to occur. Okay, I will revise this again in the next slide. Okay, see now. So A, B, C, D is your glass slab. EF is the incident ray. NN dash is the normal at the point of incidence. MM dash is another normal. So EF is incident ray. F, this G, you can say this O to O dash is your refracted ray. Okay, and from here this is the second point of refraction. Again, this and GH is your emergent ray. So again over here this is your angle of incidence I1, R1, I2, R2. We know that in the first case angle I1 is going to be greater than angle R1. In the second refraction, angle I2 is going to be less than angle R2. But as R1 and I2 being in the same medium, we can say that angle of refraction R2 will be equal to I1 because they are in the air medium, and angle of refraction R1 is going to be equal to angle of incidence I2 because they are in the glass medium. Okay, alternate interior angles, you can apply maths formula to it. Now, this is your rarer, this is your denser. We know when it passes from rarer to denser, it is going to move towards the normal. So this ray has moved towards the normal. Here it is moving from denser to rarer. So it will move away from the normal. So it is going away from the normal. So now if you just extend your original incident ray and see the difference between the emergent ray and the original incident ray, this is the difference. The emergent ray has moved back a bit. It is displaced from its original position. It is not coming the way it was supposed to come. So now this displacement is called as lateral displacement, right? Understood? You should be able to explain this entire phenomena point wise if a 3 to 4 mark question is there. Along with that, you also have to draw the diagram. Diagrams, as far as physics is concerned, all diagrams should be self-explanatory diagrams. Even if the invigilator sees your diagrams, he or she should know that no, the conceptual knowledge of the student is good. So hence, okay, if there is little bit more or less in your explanation, that can be compensated with the help of your self-explanatory diagrams, neat and clean. Okay, now we know this is a lateral shift or lateral displacement. This was the lateral shift or lateral displacement denoted by small d. Now how much will this be there? Okay, so there can be scenarios that this can be very large. There can be scenarios that this can be very small, right? So the amount of lateral displacement, the measure of lateral displacement depends on what all factors. So lateral shift or lateral displacement depends upon angle of incidence. Okay, so this depends upon this angle of incidence. Now, how is it dependent? It's directly proportional. More the angle of incidence, more will be lateral displacement. Secondly, it also depends on the refractive index of the medium. Now, this concept of refractive index we are going to learn, I mean, just like in the next slide. So, more, just for now, just keep in mind that more the refractive index, I am denoting refractive index by Ri, more the refractive index, again, more will be the lateral displacement, again, directly proportional. Again, thickness of the medium. For example, the glass slabs, okay? So the glass slabs can be thin, the glass slabs can be thick. If the glass slab is thin, there would be little lateral displacement. If the glass slab is thick, the lateral displacement is going to be more. So again, thickness of the medium, that means again all these three are directly proportional. That means as these things increase, your lateral displacement is going to increase. All right, it's going to increase. It's going to increase. Thickness of the medium. So these are the three factors on which your lateral displacement is going to be there. All the three factors are directly proportional. So more angle of incidence, more lateral shift, more refractive index of the medium, more is the lateral shift, more the thickness of the medium, more will be the lateral shift. Okay. Now, what do you mean by refrangibility? Okay, this concept is based on refraction only. Refrangibility is basically the ability of the light rays to bend on propagating from one medium to another. Refrangibility depends upon optical density of the medium. Now, why does the light, I mean, just a question must have arisen in your mind. Why is light bending? Okay, fine, there is density. Now, if you see, when we compare air and water, okay, what is air? Air is a gaseous medium, water is a liquid medium, and on comparison, glass is a solid medium. So we have studied, this is the basics, that when these mediums change, density of the medium also goes on increasing. So density is defined by mass upon volume. That means in gases, how are the molecular arrangement in gases? The molecules are sparsely available, right? One molecule is here, so another molecule will be there. In liquids, they are a little closer, okay, in liquid molecules. So that's why these gases and liquids, they are called as fluids. They can go from one place to another. But then as compared to solids, in solids, the molecular arrangement is very compact. They are compactly arranged with each other. There is no space for anything to come inside to it, right? So when a ray of light passes through gas, it gets ample amount of space to pass through gas. Now when it is passing to liquid, the density of the liquid is greater than the gaseous state. Okay, so density of water is greater than air. So when it enters the liquid medium, it does not get that much amount of space, right? So what happens is, during this thing, velocity of light, okay, velocity of light decreases. Velocity of light decreases. Obviously, this incident ray, the light is coming with a certain velocity, okay, and we know light travels in air or in vacuum with a velocity of 3 into 10 to the power 8 meter per second. So that is called as c. C is always denoted by as velocity of light in air or vacuum. Both of them almost have the same value. So velocity of light in air is 3 into 10 power 8 meter per second. When it enters a water medium or a liquid medium, this, because of the increase in optical density, these are the keywords which are to be used, right? Because of the increasing optical density, the velocity, what is velocity? Velocity is the speed. The speed of the light ray decreases. So as the speed of the light ray decreases, it bends towards the normal. Okay. Similarly, when this light ray is passing again from air, that is your rarer medium, to highly dense, now we are coming ahead with solids. Okay, now so on comparison with water, solid glass or any solid medium is more optically denser. So will the bending will be more in water or the bending will be more in glass? The bending will be more in glass because optical density of solid is greater than in liquids, right? So if you see the angle of refraction over here is, for example, you take that this can be 40 degrees. So this angle of refraction would be around 25 to 30 degrees. Okay, so that shows us that the bending is more in glass. Again, velocity of light in glass decreases. Velocity decreases. Why does it decrease? Because the optical density of the glass or the solid is way higher than the optical density of air. Okay, so this is called as refrangibility. Refrangibility means the ability of the light rays to bend on propagating. What do you mean by propagating? Propagating means traveling from one medium to another. Okay, traveling from one medium to another. So ability of the light rays to bend on propagating from one medium to another. Now this ability of bending, what does it depend upon? It depends upon optical density. Now as the optical density increases, velocity decreases. Because of the decrease in velocity, the ray of light is bent. Understood? Very, very important basic thing that you should be able to understand and you should keep in mind, because this is the base concept based on which we are going to learn about a lot of atmospheric phenomena that is taking place around us, right? Okay. Now we come to, as we had studied the laws of reflection, in the same way we are going to study laws of refraction. Okay, we know what is refraction. Refraction is bending of light when light travels from one transparent medium to another transparent medium. Secondly, when light travels from a rarer medium to a denser medium, the ray of light bend towards the normal. When it travels from a denser medium to a rarer medium, it travels or it moves away from the normal, right? So now, as far as the first law is concerned, the first law is basically almost, I mean, same to the law of reflection, which says incident ray, refracted ray, and normal to the interface of two transparent media at the point of incidence, all of them will lie in same plane, right? So like for example, this is your interface. As I told you, what is interface? Interface is always the point where the two transparent medias are meeting. So this can be air, this can be water. Okay, so now this is the ray of light which is passing from air, and it has, this is my incident ray. This is the point of incidence. At the point of incidence, what's the rule? We draw a normal, and then now this light ray has bent towards the normal. Okay, so this is air to water, it is bent towards normal. Now these three things, what all? Incident ray, refracted ray, and normal. All of they lie in the same plane. Understood? All of them lie in the same plane. Now, second law is very, very important. Second law states that, okay, we have seen now there, now over here, this would be my angle of incidence between normal and incident ray. This is my angle of incidence, and this one would be my angle of refraction. Okay, the second law says that the sine of angle of incidence to the sine, the ratio of sine of angle of incidence to the sine of angle of refraction is constant for the light of a given color, also and for a given pair of media. This law is also known as Snell's law. So it says, it basically tells us that sine, you know sine, what is sine? Sine is the trigonometric ratio. Okay, so sine of angle of, ratio of sine of angle of incidence to sine of angle of refraction. So how, I mean, you must be imagining, ma'am, how did sine trigonometry come over here? These are just rays passing from one medium to another. So how do I apply trigonometric ratios over here, right? So this is your interface. This is my incident ray. Okay, uh, be more clear with this. Okay, so let this be the interface. This is my incident ray. This is the normal. And this is my refracted ray, right? This is the angle of incidence and this is the angle of refraction. This is the point of incidence. Okay, what I do, I'll draw a perpendicular from this to this. Again, if I just extend this normal, I will draw another perpendicular from here to here. Okay, now what are these? These have become right angled triangles, and this angle of incidence or angle of refraction is my theta. And we know what is sine function. Sine theta is always opposite upon hypotenuse. So as far as opposite is concerned, this is the opposite side, this is the hypotenuse, and for this theta, this is the opposite side, this is the hypotenuse, right? So this ratio, that sine of angle of incidence upon sine of angle of refraction is always a constant. Okay, and it is constant when it is constant for a given pair of media. Given pair of media means when I'm traveling from air to water, this ratio would be constant. But when I travel from water to air, the ratio would be different. Okay, it's not vice versa. Air, water, water, air is going to be same. No, air to water. Because what is the difference? When the ray of light is traveling from air to water, bending is happening in water. Okay, but when the ray of light is traveling from water to air, bending is happening in air. Okay, so that's why this constant would be different. So that is for a given pair, that means two media, given pair of media. Okay, and color. So when we go ahead, we will know that our entire white light is made up of 7 colors and each color has a different wavelength. We'll study that in detail in the coming up classes. Okay, so now this ratio of angle of incidence to angle of refraction is always a constant. Now this ratio, this constant term is called as refractive index. Refractive index, which is denoted by N. Okay, refractive index. So now this is refractive index for a given pair of media. What does refractive index tells us? Refractive index tells us the amount of bending. More the refractive index, more will be the bending. Less the refractive index, less will be the bending. So more refractive index, more the bending, and vice versa. Okay, so this is basically the measure of your amount of bending. So what is so this entire thing is known as Snell's law. This can come as a 1-mark question. It will ask you 1 mark or 2 mark, you can say. They will ask you, explain what do you mean by Snell's law and give an expression for that. So by Snell's law, you should say it is the ratio of sine of angle of incidence to sine of angle of refraction is always constant for a given. When it is constant, you should also tell the point where it is constant. It is always constant for a given pair of media and also for the color of the media. Okay, this constant is called as refractive index for that given pair of media. This entire thing is known as Snell's law. I is the angle of incidence, R is the angle of refraction. And sin I upon sin R will always be a constant. This constant is equal to refractive index. Understood? Hope things are clear. Okay. Right. Again, we'll just repeat. If you have not understood, just try to understand what was Snell's law. Snell's law was given by Mr. Willibald Snellis. okay, who derived the entire phenomena of Snell's law, who gave an expression, or who gave us the measurement of refractive index for a given pair of media. So if you observe, a glass is there, inside the glass water is there, the red one being the incident ray, incident at the point of incidence at the interface, blue one being the refracted ray, that's the angle of refraction, and n dash is the normal. So what is refractive? We know what was Snell's law. Snell's law, sin I upon sin R is equal to constant. What is this constant? This constant is basically called as refractive index, okay, denoted by n. Now, for example, just consider that this is your medium 1, this is your medium 2, okay, this is air, this is glass. Now, where is the bending happening? Bending always happens in the second medium, okay. Over here also the bending is happening in, instead of glass I should put it as water. Bending is happening in this water medium, okay. So wherever the bending is happening, we take refractive index of that particular medium. See, so refractive index, I will say refractive index of medium 2 with respect to 1. Okay, so instead of writing this entire thing, I will write it as refractive index of medium 2 with respect to 1. This is one way of writing it. In some textbooks, they also show us refractive index of medium 2 with respect to 1. Okay, both are correct. This tells us this is refractive index of medium 2 with respect to medium 1. That is from where it is coming, and where is bending happening? Bending is always happening in the second medium. So always remember refractive index will be of the second medium, right? So this one also tells us the same thing, refractive index of medium 2 with respect to medium 1. To be precise, I can also write this as refractive index of water with respect to air. Water with respect to air, or this can be written as refractive index of water with respect to air. Okay, now I'll tell you a relationship between refractive index and velocity. Basically, it is entirely, why is this bending happening? Why is the angle of refraction changing? Because velocity decreases. Why does the velocity decreases? Because optical density is increasing, right? So let us now try to derive a relationship between refractive index, right? Your refractive index and velocity of light. But this is very, very important, because we know when light travels from rarer to denser medium, optical density is going to increase. So as optical density, I'll write this as optical density increases, velocity of light decreases. When ray of light travels from denser to rarer medium, what will happen? It is going from water or glass to air. In air, your optical density decreases because air is a less denser medium. So your velocity of light will increase. Okay. Now, in the first case, the velocity decreases, hence the ray is bent towards the normal. In the second case, velocity increases, hence the ray of light bends away from the normal. So let us see this phenomena again, and let us try to derive a relationship based on all this. See now, refractive index over here, first medium is air, second medium they have taken it glass. So we have derived a relationship which tells us refractive index of medium 2 with respect to 1 will always be equal to velocity of light in medium 1 upon velocity of light in medium 2. Okay, so this can be written as refractive index of 2 with respect to 1 is equal to V1 upon V2. Very important. Some textbooks have this formula, refractive index of 2 with respect to 1, again equal to V1 upon V2. It's the vice versa. If it is 2, 1, it will be 1 upon 2. Okay. If I say, just imagine a scenario. Again, this is going from second medium. So this is touching this interface. At this point, I am drawing a normal, and now it is going away from the interface, right? In this medium, it is going from second medium to first medium. Okay, so can I write this as, now where is the bending? Now this is another refraction, 2 to 1. This is another, this was one refraction which we explained it over here. This is another refraction. So in this refraction, in the second refraction, where is the bending happening? The bending is happening in this first medium. Okay, so it would be refractive index of medium 1 with respect to 2, or it can also be written as refractive index of medium 1 with respect to 2. With respect to will always be the medium from where it is coming, and refractive index will always be of the medium in which it is bending. Just keep this in your mind. Okay, so now this will be equal to V2 upon V1. 1 to 2 upon 1. 1 to 2 upon 1. Over here, 2, 1, 1 upon 2. This is the way you remember it. Okay, very, very, very important from exam point of view and from numerical part. So this refractive index, some textbooks also denote it as nu, some textbooks denote it as n. Okay, so whatever is the symbol, formula will remain same. Velocity in first, refractive index of 2 with respect to 1 is equal to velocity in first medium upon velocity in second medium. Understood? Hope everything is clear. Okay, now we come to another term that is called as absolute refractive index. Now, what do we mean by absolute refractive index? Absolute refractive index is when the first medium is always either vacuum or it is air. Okay, first medium is either always vacuum or air. So that means the ray of light, whichever, so these are the different types of medium. If you see, water, alcohol, kerosene, fused quartz is a type of glass, turpentine oil, benzene, crown glass, Canada balsam, rock salt, all these are different mediums. So what is given there, different refractive indexes are given. Now where, how are these refractive index measured? These are measured when the ray of light was always with respect to either vacuum or air. So that means the first medium was always vacuum air and the second medium was these. Right, so this type of refractive index is called as absolute refractive index. That is the ratio of velocity of light in vacuum to that of the velocity of light in that particular medium. So this can be your, this is your medium, any medium of these two, and this will always be vacuum or air. The first medium always needs to be vacuum or air. So ray of light, obviously air is the rarest medium that we have. Okay, there is no other medium rarer than air or vacuum. So can I say that velocity of light in air or vacuum will be highest because its optical density is lowest? Yes, right? So velocity of, this is the ray which is passing again, so it has to pass through the medium up towards the normal. So when it is passing towards the normal, so can I say that refractive index of the medium will always be equal to velocity of light in air or vacuum upon velocity of light in that particular medium. So velocity of light in vacuum is always denoted by c, and we know what is c. So velocity of light in air or vacuum, it is 3 into 10 to the power 8 meter per second. Very, very important. Okay, sometimes in numericals this value is not given, so you need to learn this, new to keep this in mind, that velocity of air or vacuum, of light in air or vacuum, is equal to 3 into 10 to the power 8 meter per second. Understood? This is called as your absolute refractive index. Now, one more thing to just ponder, just observe the refractive indexes of these different media, right? So if you see, what is the refractive index of air? It is 10003, because the velocity, this is the velocity of light in vacuum. So if you compare sometimes the velocity of light in air, it comes to be 2.997 into 3 to the power 8. So that's why it is, both of them are approximated to the same value, right? So refractive index is very small. Ice, it is 1.31, alcohol 1.33. Some things I'll tell you to learn. Always learn, keep in mind refractive index of water, refractive index of, you can say, benzene, or you can say fuel quartz, that's glass, and diamond. Okay, crown glass, diamond. Diamond is the only solid which has the highest refractive index. Highest. There is no other solid which has a refractive index more than diamond, right? So can you tell me, how is refractive index and bending related? I had told you in the first, like just 5 minutes before, that more the refractive index, more will be the bending. Right. So how will the bending happen in diamond? How is the refractive index of diamond? Refractive index of diamond is highest as possible, 2.42. So the bending of light in diamond will be the highest. So that means, for example, if I just consider this to be a diamond, why diamond is such a precious gem? Why not other gems in place of diamond are so precious than diamond? So for example, this is your diamond. If one ray, if just a ray of light passes into the diamond, okay, what will happen is, this ray of light, for example, this can be your this thing, normal, and this ray of light will bend so much that it won't be able to go outside, and it would get totally, again we are going to study this phenomena, it is going to get totally internally reflected. TIR, we call it total internal reflection, and hence only one ray is enough for the diamond to get illuminated from inside. Okay, more illumination, sparkling effect. So that's why diamonds are so sparkling. Okay, illuminating effect, more illumination. Understood? So two things, refractive index of diamond is very high, and it will support total internal reflection. The phenomena of total internal reflection we are going to study in the coming up episodes. Okay, now just for now, just keep it in mind that if refractive index of the medium is higher, then velocity of light in that medium will be relatively less. So there is a comparison. More the refractive index, less is the velocity of light, more will be the bending. So just to go step by step, we can just summarize this. You can say, more the optical density, that means more optical density, what will happen? Lesser will be the velocity. Lesser the velocity, more will be the refractive index. More refractive index, more will be the bending of light. Okay, this is just in a nutshell what we did. Okay, remember these small things. Understood? Okay, so now based on this, let us try, there's one more thing to it, principle of reversibility. Now what do you mean by principle of reversibility? If you see, see these two things. This is air medium, this is your water medium. The ray of light is passing from air medium to water medium. It is getting bent towards normal. In the second thing, what is happening in the media, pair of media are same. That now the ray of light is passing from water medium to air medium. Okay, so if the ray of light travels from medium 1 to medium 2 along a certain path, it has to follow the same path when it is traveling from medium 2 to medium 1, right? So that means, can I say the measures of my angle of incidences and angle of refractions are going to be same? Now for here, this will be my angle of incidence, and for here, this will be my angle of refraction. So if I compare refractive index, for example, this will be, because where is the bending happening? Bending is happening is 2 medium. From where is the ray coming? Ray is coming from 1. So I will write refractive index of 2 with respect to 1 equal to, let the velocity of light in medium 1 be v1, velocity of light in medium 2 be v2, right? So 2 with respect to 1 is going to be v1 upon v2. And now this is my medium 2 and this is my medium 1. Where is the bending happening? Bending is happening in medium 1. And from where is it coming? It is coming from medium 2. So refractive index of 1 with respect to 2 is going to be velocity of light in medium 2 upon velocity of light in medium 1. So when I compare these two, 2 with respect to 1 and 1 with respect to 2, I get a relationship. So I can say that refractive index of 2 with respect to 1, what is it? It is v1 upon v2. So if I take this v1 over here, can I write this as refractive index of 2 with respect to 1 upon v2 divided by v1? And what is this v2 divided by v1? This is this. So refractive index of 2 with respect to 1 is equal to 1 upon refractive index of 1 with respect to 2. This is your principle. As far as your refractive indices are concerned, this is your principle of reversibility. Okay, so when I have the same medium, so I'll take with the examples of the medium, consider air to water, water to glass. So can I say refractive index of water with respect to air is equal to 1 upon refractive index of air with respect to water. This is the formula for that. Okay, for that matter, if I have water and glass, I can say refractive index of water with respect to glass will be equal to 1 upon refractive index of glass with respect to water. Okay, it's the reciprocal of each other, right? As it is going to follow the same path, the values of angle of incidences and angle of refractions are going to be interchanged and the values will be same. Okay, magnitude will be same, only incident angle of incidence will become refraction next, and angle of refraction over here will become angle of incidence. This is your principle of reversibility. Understood? Okay, let's move ahead. Now, based on this entire phenomena, let us try to solve some questions. Okay, refractive index questions, because these can come, I mean, 1 or 2 are bound to come in our board examinations. Okay, so let's see. It tells us that the first one, absolute refractive index of water is, okay, just observe, it says absolute refractive index of water is 1.36. What is the velocity of light in water? Absolute refractive index of water, that means it is always with respect to air or vacuum, right? So we will write it as what is given, 1.36. It's given velocity of light in vacuum, so C 3 into 10 to the power 8 meter per second. What is to be found? We have to find the velocity of light in water. Okay. Now, according to our formula, we know refractive index of water with respect to vacuum will always be velocity of light in vacuum upon velocity of light in water. So just substitute the values now. This is given as 1.36, which is equal to 3 into 10 to the power 8 meter per second, the whole upon velocity of light in water. So therefore, velocity of light in water is equal to 3 into 10 to the power 8 meter per second divided by 1.36. Right? So now can you divide 3 divided by 1.36 will be, so it comes out to be 2.2 10 to the power 8 meter per second. So hence we can write a statement at the end that the velocity of light in water is 2.2 into 10 to the power 8 meter per second. Okay, this is the way you should be solving your numericals. Secondly, Let us solve this one as well. Light travels with a velocity of 1.5 10 power 8 meters per second in a medium. So they have just given us velocity of light in a medium. That's 1.5 10 to the power 8 meter per second. On entering the second medium, so let this be medium 1. So velocity of light in medium 2, they have given as 0.75 into 10 to the power 8 meter per second. What is the refractive index of second medium with respect to the first medium? So we need to find refractive second with respect to 1. We know refractive index of medium 2 with respect to 1 is equal to, now again, in some students do not get confused, because it might happen that in your textbook it must have given refractive index of 2 with respect to 1. Okay, it's one and the same thing, can be used in an interchangeable form. 2 with respect to 1 is equal to velocity of light in 1 upon 2. So what is velocity of light in medium 1? They have given as 1.5 10 to the power 8 meter per second divided by 0.75 10 to the power 8 meter per second. Now 10 power 8, 10 power 8 cancel. 75 and 1.5 will go by 2. Hence the refractive index of 2, medium 2 with respect to 1 will be 2. Now will there be a unit for refractive index? No, refractive index does not have any unit, because it is the same quantity upon same quantity, right? So meter per second and meter per second are also going to be get cancelled. So it will only be a value, a numerical value. So the refractive index of the second medium with respect to the first medium is going to be 2. Okay. The third one says, if the speed of light in a medium is 1.5 10 to the power 8, what is the absolute refractive index of the medium? It's again same. Okay. So refractive index, absolute refractive index of a medium is, we know, velocity of light in vacuum upon velocity of light in that particular medium. In vacuum, we know it is 3 into 10 to the power 8 meter per second, and velocity of light in this medium is given as 1.5 into 10 to the power 8 meter per second, right? So 10 power 8, 10 power 8 cancel, 3 divided by 1.5, hence refractive index of that particular medium will be 2. Understood? Now, okay, this one is a good question. If the absolute refractive indices of glass and water, so now they have given refractive index of glass is 3 by 2 and refractive index of water is 4 by 3. Okay, we need to find refractive index of glass with respect to water, or some textbooks might say refractive index of glass with respect to water. Okay, so when only refractive indices are given, what do we do? Refractive index of glass with respect to water will be absolute refractive index of glass upon absolute refractive index of water. This is the formula when only refractive indices are given, right? Okay, so now how will we work this out? How did we arrive at this formula? So just put in the velocities. So I know refractive index, this refractive index of glass is given. Okay, so glass with respect to water. What is refractive index of glass given as? 3 divided by 2 upon refractive index of water 4 divided by 3. So this is going to be 3 by 2 into, this will become reciprocal when it will go up, 3 by 4. So it's going to be 9 upon 8. Hence, refractive index of glass with respect to water is 9 divided by 3. You can just divide it and it will come 1 point something. If the vice versa would have asked, if they would have asked, I mean, I'm just going away from the question. If the question would have asked, find out the refractive index of water with respect to glass, nothing you have to do, you just have to take reciprocal. So it will be 1 upon 9 divided by 8, which is going to be 8 upon 9. Water with respect to glass will be 8 upon 9. That's the, what is this? We just studied that. It's the principle of reversibility for a given pair of media. Okay, are the mediums changing? No, they are same, glass, water, water, glass. So hence the refractive indices of both with respect to each other will be vice versa of each other, reciprocals. Okay, now. Okay, one more last question. It says light enters air to glass having refractive index 1.5, refractive index of air to glass. So that means it will be refractive index of glass with respect to air. It's 1.5. Speed of light, we need to find the speed of light. G we need to find, and C has been given to you 3 into 10 to the power 8 meter per second. So as your question goes, refractive index of glass with respect to air will be velocity in air, that is your C, upon velocity in glass. So that's 1.5 equal to 3 into 10 to the power 8 meter per second whole upon Vg. So that's velocity of light in glass will be 3 divided by 1.5 into 10 to the power 8 meter per second. So hence velocity in glass is going to be 2 into 10 to the power 8 meter per second. That's your answer. Okay. Hope you have understood the entire phenomena of refractive index, refraction. Very, very important, because we in the next coming up classes we are going to study about the atmospheric refraction. So unless and until your this base is not strong, we won't be able to do it. Okay, coming up next class we have lenses. Okay, we will study lenses, different types of lenses, convex and concave. We will study image formations of lenses, just the way we did our convex and concave mirrors, right? So that is going to be our next agenda. Thank you. Hope you are following the videos. See you soon. Bye bye, take care.